All right, so in our last screencast for spectroscopy period, really, we are going to do two examples of some NMR spectroscopy and determining unknowns from our spectra that we're given. Here is some, I just like to list out the really important information that you can get from each type of spectra. So from your proton spectra, you should be able, the really important things you should get are the number of signals, right? The total number of signals gives you the number of chemically distinct protons. You should get a chemical shift, and that tells you things like if you've got aromatic rings, double bonds, or electronegative atoms. Your packet is not going to have integration, but some of your homework problems will, because we want to make sure that you do still know how to do integration. And then splitting patterns are incredibly helpful because they tell you the neighboring protons. Now, information that we obtain in carbon-13 NMR are the number of signals in the chemical shift, right? So we're not going to have splitting and we're not going to have integration per se. So let's look at some examples. I'm going to do a proton NMR first. I'm going to determine the number of proton signals. I'm going to analyze the chemical shifts, and I'm going to have integration here, and then we're going to interpret the splitting patterns, and then we're going to try to piece together some molecular fragments. So let's look at our unknown spectra. So here's our unknown spectra. When we look at this, what's really nice is we have the chemical formula. It's C10H12O2. Look, and as I look at this, I want to evaluate a few things. One of the things that I can see here is that we really have kind of four distinct areas, right? We've got a triplet here. We have, so that's a triplet. That's a multiplet. I think he calls it a sextet, but it's really a multiplet. Then we've got another triplet here. And then this mess down here, that indicates an aromatic ring. So when you look through your packet, if you see kind of a mess down there, that's what we're looking at as the aromatic ring. So the first thing I do is I sit down and I identify, do I have triplets, multiplets, and so on and so forth. So the next thing I'm going to do is say, okay, hey, look, this guy right here, he is, whatever proton this is next to a CH2, right? Because that's what's going to give us our splitting. Now, I'm going to look at the integration here, and if I add that up, 2.5 plus 1 plus 1 plus 1.5, that gives me 6. No, yes? Had to take a moment and double check my math. That gives me 6 protons. And if I take that, multiply that by 2, that's where I get my 12 protons from that match right here. So what this tells me is this integration here is really 3. And that's really 2. And that's really 2. And that's really 5. Now, that 5 there is going to match really nicely with an aromatic ring. So if I have an aromatic ring and I have something over here that's attached, I end up with 1, 2, 3, 4, 5 protons. So I know that that is one piece of my spectra. The next thing I'm going to look at here is that triplet. If that is 3, there's my 3. That's going to be next to a CH2. So the triplet is this peak shown in red, and it's next to a CH2. Over here, right, this is also going to be next to 2 hydrogens. It's not going to be split in any way, it doesn't look like. So this is a CH2. And I bet it is next to a CH2 as well, if I had to guess. And so there's the red peak there. And now this multiplet, When we look at this multiplet, it's caused by 2. It's a CH2 here, but my guess is it's the middle, right? So it's the middle fragment. This one's going to be on the end. If I had to guess, I'm going to bet that sucker's right there. That's the CH2 there. And then this is another CH2. And then there's the aromatic compound. So I would say if I want to piece this together, my guess would be it looks something like, oh, there's 2 oxygens in there. Yeah, so we need to think through where those oxygens would be. So at this stage, making a table is probably going to be pretty helpful. So let's look at our table. So this is a table from what you can see. We've got some of the pieces that I put together as well, right? So there's that CH3, CH2. There's a CH2 in between, probably a CH3 and a CH2. And then here's another CH2. And then there's probably an oxygen attached. It's one of the reasons why that's so downfield. And we get this 4.2 there. That's pretty far down. And then an aromatic ring. So when we're putting these pieces together, right, you can see kind of how these are generating other additional signals. And then you can break this and see where things would be. This is the unknown and the pieces that are put together for the unknown, where the only thing that really makes sense is to put a double bond O here. We know there are 2 oxygens from the original chemical formula that we were given. This is where your IR is going to be really helpful, right? Because your IR is going to say, hey, look, you've got an ester stretch, okay? So you're going to have some oxygens. They're not going to be alcohols. You can double check this molecular weight with your mass spectrometry. So there's going to be a lot of pieces that you have that are really helpful to figuring out your unknowns. Let's do a second one. So the next one is we're going to do a carbon-13. With this carbon-13, we are also going to have some additional information. So we're going to determine the number of carbon signals. We're going to look at the shifts, and then we're going to build molecular fragments just like we did before. Now, here are some beautiful things. We have a IR spectra with this. We've also been given the depth spectroscopy, which indicates the type of carbon generated by each signal, right? So we have a CH3 that generates this signal. We have a carbon that generates that signal, and then we have a CH2 that generates that signal. Now notice we have 5 carbons in this unknown and 1 oxygen. When we look at these 5 carbons, we only really are given 1, 2, 3 carbons here. And that's a really good indication that we are going to have some equivalent carbons, okay? And so that's something to really watch out for. Now, one of the big take-homes from the IR here should be that we have an alcohol group. That's super duper exciting. Now this, right, is just going to be that CH that we're always going to get, but we do end up with an alcohol group here. So that is a really great point of reference that we have to really, really help us out. So just like we did for the NMR Spectra, let's see if we can get some kind of molecular fragments here. So if we know we're going to end up with a CH3, okay? We know we're going to end up with a carbon, right, that doesn't have any hydrogens attached to it. And then we know we're going to end up with a CH2, okay? Now, this CH2 here is quite downfield, so it's more than likely that that's going to be the one that's attached to the alcohol group, right? Because it's so far downfield. That carbon, my guess, is going to be in the middle, right? And then this one's going to be the farthest away from the alcohol. So when we look at this, right, and look at all our pieces, we've got a CH3C, and that's got that chemical shift that's farthest away. We have some sort of C that's in the middle, and then we've got a CH2 with an OH. So if we piece together these, right, we can see that there are our signals, and then we can bring these together to show that, hey, look, if you've got this one, and this one, all of those in blue there are equivalent, right? And that's 1, 2, 3, 4, 5 carbons, but that's consistent with only 3 peaks in the spectra, okay? Then we've got our HOCH2 and then our carbon all by itself. Now, at this stage, we are done with spectroscopy. We will have some review in class as well as a Plicker review day. And then we will also have time to work on our projects.